Again, Mr. Chairman, and thank you for being here. I'm Pietro Foti, I'm a postdoc at La Sapienza University of Rome, and today I'm going to talk about the blunt and sharp notches, and in particular, the distinction between blunt and sharp notches as it can be interpreted through the average SED method, of which I'm going to talk about later. Regarding the aims of this work, we wanted to show that the average SED method is actually capable of properly account for both sharp and blunt notches, capturing well-known trends linked to the notch effect. Of course, as many of you probably know, this method has been widely validated to account for both blunt and sharp notches. But in these cases, we wanted to see if the method was actually able to capture all the trend from going from blunt notches to sharp notches. And we also wanted to derive a limit condition to distinguish sharp and blunt notches in terms of a notch radius. This concept, I have to say, is not new. You can already find it in literature, but we wanted to reinterpret this concept according to this method. In order to do so, what we have done is to carry out some parametric finite element simulation in which we have applied the method for a generic material that we identified uniquely through the parameter R0 that is actually a material parameter according to the method itself. And finally, of course, we have carried out also an experimental validation through a fatigue strength reduction factor database that we have retrieved from literature. So first of all, I will talk about the distinction between the sharp and blunt notches. You are probably familiar with the Frost and Miller diagram, in which what we can see here is that when dealing with notches, we have two different behaviors. First of all, we have a decreasing trend with the increasing stress concentration factor. And in this case, we are dealing with blunt notches, so-called blunt notches, because we can account for the notch effect by simply dividing the fatigue limit of the material by the stress concentration factor. At a certain point that is called the branch point, we will have an horizontal asymptote, and in this case, the stress concentration factor will actually overestimate the effect of the notch on the fatigue properties. In this case, we need to deal with the notch effect with some more advanced concept, and in particular with the true fracture mechanics or through methods that are derived from fracture mechanics concept, such as in terms of stress, we have as an example the theory of critical distances. And in terms of energy, we can deal with this zone of the diagram with the strain energy density method, as an example. I reported here also the Kitagawa diagram that actually deals with defects. And as you can see here, in this diagram, there is a distinction within cracks that are divided by a parameter R0 that it is the LADAD parameter. And we are having that for cracks lower, having a size lower than A0, we are dealing with the short cracks that doesn't affect so much the fatigue limit, while for long crack, we have to deal with them through the through fracture mechanics. I show you this diagram because at the beginning, around 2003, Azzori and Lazzarin proposed that both diagrams could be thought as a part of a more complex diagram that would involve both sharp, that would consider short cracks, long cracks, and the notch effect through a unique diagram. In this case, they were dealing with a notch having parallel flank and finite radius. And actually, with increasing the depth, you are also increasing the radius at the notch tip. So at a certain point, you will have that you can deal with this notch through the stress concentration factor because this will become a blunt notch, actually. Another way to represent all this is to just normalize the axis of through the limit value of the stress concentration factor, and you will obtain that for values lower than the limit value of the stress lower than the stress the limit value of the stress concentration factor, you are dealing with the blunt notches, while for higher value than the limit stress concentration factor, you are dealing with the sharp notches. So let's talk about the method that we wanted to consider in this work, the SED method. First of all, some basic knowledge about this method. As you can see, it has been validated during the last 25 years for dealing with both fracture in static condition and fatigue failure. And the basic idea behind this method is quite simple. It assumes that the failure happens when the local strain energy density averaged in a given control volume will reach a critical value. Here I reported the case of a static failure for an ideal brittle material. In this case, we are able to evaluate this value of the critical energy density just through the ultimate tensile strength. An important thing to say about the critical value of the strain energy density is that this is assumed to be independent on the notch opening angle, the loading condition, and the local geometry. In this case, it's independent on the blunt or sharp notches. It can deal with both. So we start thinking if, since the method can account for both sharp and blunt notches, probably it could be able to, it could have inside the method a condition to discriminate between sharp and blunt notches. So first of all, I need to talk to you about the control volume, because we have focusing on this to define this limit condition. And the control volume, as you can see here, has a shape that depends on the local geometry. In particular, if we are having a zero radius notch, the control volume is just a sector-shaped cylinder centered at the point of stress singularity. While if you are dealing with the blunt notch, you will have that this the control volume position will change with the loading condition, and it has actually a different shape. As you can see here, is a crescent moon-like shape. While finally, this control volume is characterized by a characteristic length, R0, that, as you can see here, it can be evaluated through the material parameter. In this case, for static condition, you will have the fracture toughness and the ultimate tensile strength. While I will talk later about the case of fatigue, this method can be applied through fatigue problems by two assumptions. The first assumption is that the fatigue failure happens in the high cycle regime, absent in the linear axis regimes, as shown a brittle nature. As you can see, through this method, you can also account for different effects that are known to influence the fatigue behavior, such as the load ratio effect, or different. You can deal also with different failure initiation points, such as from the weld. In this case, I reported the case of weldments because it's the most famous and the first one that has been done to apply the method. And you can also account for different loading conditions. Now, the first condition that we wanted to consider when dealing as a possible limiting condition to distinguish between blunt and sharp notches was to consider the way the control volume can be defined when dealing with notches having a finite radius. As you can see here, there is the control volume in this case could assume two different shapes actually. The first one here is ending on the crack edges, while the second one here is ending on the part of the notch that is as a curvature. So we thought that maybe a possible limiting condition would be the one that differentiates between these two conditions. You can see here that the problem could be easily schematized, and we have been able to derive the value of the notch radius that discriminates between these two conditions analytically. But here we reported a simplified expression because the analytical one was a bit longer and probably not so easy to be used. But it's a quite good fit, I can assure. So we needed to test this condition. And in order to do so, we carried out some simulation by some parametric simulation, changing all the component geometry parameter, considering different R0 values going from 0.1 to 1 millimeter, and changing also the Poisson ratio. In order to evaluate the validity of our limit condition, we needed to find a way to estimate the KF value. Actually, starting from the equation that defines the methods, it is possible to easily obtain that the fatigue strength reduction factor should be equal at the square root of 2 times the Young modulus times W1 R0, where W1 R0 is actually the value of the average strain energy density in a given control volume of radius R0 for the application of a nominal of unit remote load. In this case, you can easily evaluate KF. So now we have everything to validate our assumption. So we have conducted our analysis, and we reported first the results in these graphs, where we have on the y axis the ratio between the stress concentration factor and the estimated value of the fatigue strength reduction factor, plotted against this the limit condition that we have assumed, the ratio between the limit condition and the actual notch radius. As you can see, this condition is able to somehow find a point where the notch starts behaving as a sharp notch, but it's not representing the conventional condition that we are used to when dealing with the definition of sharp and black notches, because like dealing with this sort of diagram, the conventional limit condition would be could be found by the intersection of the two asymptotes that you can see here, where this asymptote is relative to the blunt notches, and this other asymptote is relative to the sharp notches. So the first condition that we have evaluated didn't work so well, but obviously we thought that we can like fit this value, and in a subsequent analysis, we have fitted the limit condition that could be found through the previous diagrams, and we obtained that the limit condition should be equal to this equation here, that for now is fitted, but we also managed to find somehow an analytical solution for this. And as you can see, now the limit condition in terms of radius is actually a function of the notch opening angle, the Poisson ratio, and the characteristic value of the characteristic length of the R0. As you can see here, it is also possible to define some equation to foresee the value of the fatigue strength reduction factor, starting from the stress concentration factor and the ratio between the limit condition and the actual notch, the actual radius notch. Finally, we can also plot these results through another, the last diagram that I've showed you before. And as you can see, it's possible to capture through this limit condition the distinction between blunt notches that are in this graph on the left side and sharp notches that are on the right side. In this case, this equation is already available in literature, to be honest. What we have done is to estimate the limit value of the stress concentration factor by replacing to the actual geometry the value of the limit notch radius. And as you can see, in terms of numerical simulation, appear to work. So now we had to prove our concept through an experimental validation, because of course, up to now, we were just talking about numerical simulations. So what we have done is to collect a fatigue strength reduction database that is accounting for more than 700 data. And it involves different kind of materials, as you can see here. Some of the geometry, to be honest, are not exactly mode 1 in mode 1 condition, like this one and this one. It's not exactly on mode 1 condition, but we have considered also them. Here you can see the fatigue strength reduction database that we have retrieved in terms of ratio between the stress concentration factor and the fatigue strength reduction factor, plotted against the reciprocal of the notch radius, and in terms of the reciprocal of the fatigue strength reduction factor and the stress concentration factor. So very briefly, you can see here how this the data set is accounted for by the first equation that we have proposed, and apparently is able to capture the limit condition between sharp and blunt notches, blunt and sharp notches, for different opening angles, because in this case the inclination of the oblique asymptote is changing with the notch opening angle. And in this case, you can see how the second equation that we proposed works in defining the limit condition between blunt and sharp notches. Finally, here you can see a comparison in terms of estimated fatigue strength reduction factor and actual fatigue strength reduction factor for the first condition, for the first equation that we have proposed, the second equation that we have proposed, and for the conventional way to apply the SED method. So, to conclude, we have find somehow a condition to distinguish between blunt and sharp notches easily based just on a geometrical parameter. So actually, when you could somehow establish if a notch will behave as a sharp one or as a blunt one, just without comparing some geometrical parameter, without doing any simulation. And we have shown that the SED method is able to capture all the trend of the curve defining the notch effect, going from blunt notch to sharp notch. And in this way, you could also have a possibility to establish, according to just geometrical consideration, whether improvements are expected on the fatigue behavior of a component by just acting on the notch radius. With this, I conclude, and I thank you for your attention.